going to do the heat equation, okay? So this is dealing with conduction, okay? So we're going to use the COE and Fourier's law, which gets us the heat equation, okay? So Fourier's law and COE gets us the heat equation. So it's dealing with conduction when we have a solid medium and looking at the energy inside of it, okay? All right, so we already a little bit talked about Fourier's law, right? It deals with conduction, heat flux, and it's from the temperature distribution in that medium, okay? So we have the vector form of the equation right here being shown. The negative that we have in Fourier's law tells us that heat transfer occurs in the direction of decreasing temperature, okay? Thermal conductivity can be solved, if we apply Fourier's law and move it around, we can get solved for thermal conductivity. So if you wanted to get the thermal conductivity of substance, you create an apparatus where you control the heat flux and measure the delta T, and you now get thermal conductivity of that substance, okay? Heat transfer, you can look at in a block of something, let's say, you would look at the isotherms to tell you the direction of heat transfer. So if you were to do a, let's say, FEA that you have for a class of kind of like a computer simulation, what you're going to get out of it when you use on a solid block of something, you're going to get, the temperature distribution throughout this block that you're looking at. Well, those lines tell you about the direction of heat transfer, okay? So if you have constant temperature lines throughout something, your direction of heat transfer is normal to that surface, and you could then split it up into components like X and Y and Z. Or if you're in radial, cylindrical coordinates, you have radial and that. Okay, so here you see those then different coordinates that you could split it up in. Okay, so you have your heat flux, and if it's Cartesian is the best coordinate system to use, then you'd have X, Y, and Z, right? And they all look pretty much the same except for the dimension X, Y, Z, right? The I, J, K. Cylindrical, right? The Z term looks about the same as above, right? This is the same as what we see in the Cartesian because that's in the direction, if you're looking at a cylinder and you're going in this direction, that's the Z direction, which is going to look like the same as Cartesian, right? Now, if we have the radial direction, so we're looking in this direction in this cylinder, we have our coordinate there, right? If we were looking for heat transfer in this direction, okay, then that would be in our angle direction here, okay? Spherical coordinates have a little bit trickier because there's two angles now, okay? So now you have the two angles that look like the cylindrical, but then you also have, the two coordinates that look like the cylindrical, and then you have another one with angles, so it becomes tricky. The one thing you'll see with the angle ones is they have the R, right, in this case, because it's got units of, this is, let's say, Kelvin, and this is meter, right? Can't have just the angle there, that would be Kelvin over degree or something like that, right? So when you actually solve for these components, it still has that, just like here, has that R, which gives that unit of length. Okay, and that's what you see kind of mentioned right here. All right, some of the common things for heat rate, one dimension, radial direction. In a cylinder or sphere, so it's in that radial direction that, right, if we have this cylinder, the radial direction is right here, okay, and if we're just looking at the heat transfer in that radial direction, we don't care about the Z or in the angle direction, then we can look at it as just the surface area. Let's say we're looking at the outer surface. Then this is the area times the heat flux in the radial, and we have a nice equation for the surface area. And one thing we do a lot with cylindrical coordinates is this prime that you see here. And all that is taking the QR and dividing it by length gives you QR prime. So that's why in here you don't see the length that's right here. Okay, and what's that's useful is because that's just a scalar. You know, you're just making the cylinder smaller. Okay, right? If you're thinking about 10 meters of wire versus 100 meters of wire, all that is a scalar of the lengths on that in that direction. So that's why we could just do it per unit length instead. Okay. Sphere, you know, sphere doesn't have a prime to it because we have that in the radial direction. You have your surface area again, but there's not, you know, it has two angular coordinates, so we have to always kind of include that surface area, so we can't divide even length out. Right? All right, so then the big one in chapter 2, which I'm told is the hardest chapter in the book, maybe the radiation chapter at the end, but this one ends up, you know, it has math. It's a heavy math book chapter. So one of the things the students have mentioned to me in the past is chapter 2 is more of understanding the equation. Chapter 3, we simplify the equation and apply it different ways to problems. Well, what they'll do is they'll work on chapter 2, try to understand it, do chapter 3, and then work on chapter 3, and then go back to chapter 2 and actually understand it even more because they're so linked. Those two chapters, they get a better understanding of chapter 2 when they've done after they've done chapter 3 also. Okay. All right. So the heat equation. So we're going to do this derivation. Okay. And that's taking, this cube. We're going to take this small little cube right here, and it's zoomed right here, and we're going to apply the conservation of energy and Fourier's law and get our equation down here. Okay. Uh-oh. Okay, here we go. All right, so if I take that cube, I'm going to put it here. And then I said we're going to start with the COE, right? Of course, in my classes, right? So we're going to start with the COE. All right, so we have our conservation of energy, right? What do we think our terms are that are going, that is the energy in and energy out?
Qx, y, qz are all n, and then plus dx, dz, dy are all.
Yep. Okay. So just looking at our block, our little tiny cube, right, of metal, let's say, and we have on that tiny cube we have some qx in, and in the x direction on the other side of the cube we have qx plus dx out, right? So let's put those in. Okay. So we have all the ins. And then we have the out, right? Let's make that a little neater. Okay. Now on our cube, we see energy generated labeled, right? But we can simplify this a little bit in that we make it energy generated per unit volume, okay? This Q dot. And then means we have to multiply times volume to get the units right. And the volume in this case is dx, dy, dz, right? Because that's our little units. That's our size of our cube. The energy stored part, we've already kind of simplified this in the other problems. So if it's incompressible, we have density, specific heat, and then our volume again, right? And then this is going to be partial. Partial temperature with respect to time. So as a reminder, this is volume, just like this one. Okay. All right, next, what we want to do is try to understand what this is, our qx plus dx. So these terms. And we're going to use a Taylor series expansion. And you probably see this or have seen it in other classes used across a cube. It's a very common thing. So our qx plus dx. So on the right side of this cube versus the left side, right, on the x direction, we start with qx, and it's any change in that partial change of that qx with respect in the x direction, okay? And we can do the same thing in the y and the z. Okay. Now we have what those terms are. We can plug them into our equation above, right? Into this equation. And now we still have the volumetric heating. And the energy stored term, right? So what's our simplification here?
You can cancel out the q's.
Yeah, so minus qx, y, minus qy, z, minus qz, okay? All right, so let's rewrite it so I can remember to have that negative sign that still gets put in front of these other ones. Okay. So then last, we got to substitute something in for QX, QY, and QZ. Okay. And so far, we've only done conservation energy on this cube and a Taylor series expansion. So what was the other thing I said that we would be using on this? What main law?
Fourier's law.
Yeah, Fourier's law now. Okay, so now we're putting in that Fourier's law, right? So now it's telling us it's conduction through a solid where this is applied to, okay? And QX, so it's QX and not conduction heat, not conduction heat flux, right? So that means we got to include the area. So the cross-sectional area for X would be this, right? Which is dy dz, okay? And then Y would be, so we have Y across this, so Y would be dx dz, and Z we have through this area, which is dy dx, okay? So that'll be our different ones here. So for X, we had dy dz as our area that it's going through, and then dt dx, partial temperature with respect to X. And we do the same thing like for Y and Z, but again with a different cross-sectional area. Okay, so now we can substitute because we didn't want to make our equation too small, right? We want to get it back to being a giant equation. We have the Z term, okay. Oop, that's not partial. All right, so now we still have volumetric heating and energy stored. All right, so next thing, what can we cancel?
Volume.
Yeah, the volume, right? So what we see here is this cross-sectional area here does not change along the X, right? It's the same cross-sectional area as you go through that little cube. So that can get pulled out of this partial, right? Same with this one, can get pulled here, here. Okay, so that means then dx, dy, dz is everywhere, and we can cancel it. Okay. All right. So that is our heat equation. In the Cartesian coordinates. Okay, any questions so far? All right, so
sorry.
Go ahead.
I'll honestly back to like the very beginning. The q dot dx dy dz, was that the that was the EG term?
Yes.
Okay.
Yeah, so that's the energy generated. Yep. Okay. Yeah, so that'll have units of, heat energy per volume, right? All right, so then we have this, and this is the full one before applying any assumptions to it other than it's the Cartesian, right, for Cartesian coordinates. So then we'll go through and apply, some simplifications. First one that we'll see a lot is constant properties. What do we think that does to this main heat equation? What's showing a property that changes in the general form of the heat equation right here? What property is showing that it could change with a direction?
Temperature?
Not temperature. Thermal conductivity. Yeah. So that K, if it's going to be constant, we can pull that out. It's not changing as a function of X, Y, or Z. Okay. So in this version that I show above, that's where you could have, a thermal conductivity that changed through a material. Let's say you were talking about carbon fiber or something, because it has layers and interwoven things that it's not so easy to put one single value to something like that. Then it could have a K value that's changing in different directions and dimensions, right? And then we would include that. But with other materials, we can say constant properties, and that pulls K out. Okay, so that makes things, and I'm dividing K. So I pulled it out of each of them and then divided it. Okay, so that means now the K is over here for dividing the energy generation per unit volume, and then it's over here, this. And this term right here can be simplified to 1 over diffusivity. That's what this term is. So it's not the absorptivity that you saw in the last problem, unfortunately, and got to use a similar symbol for the diffusivity. Which is K over rho C. Okay.
I think you missed the square for the Z portion.
Z, yes, yeah, thank you. So thermal diffusivity, okay? All right, so that's constant properties. All right, let's say there's no generation. So constant properties and, say, and no generation. All right, so then that simplifies to this. Okay. All right. Now let's say constant properties, no generation, in one dimension. So we have that. Okay. Now let's say constant properties, no generation, 1D, and steady state. Then we have this. Okay. And if we were to integrate that twice for temperature, right, that equation, it'd be a line, right? It'd be an equation of a line if we integrated that twice. Temperature would look like as a function of x. All right. Any questions?
So can you scroll up for a second?
I don't know how far.
That's perfect.
Okay. All right. So then, any other questions? Then I'll go back to the slide. Okay. So, oh, go
Are
ahead.
all of these constant properties and like one dimensional and then constant properties and no generation?
Yeah.
Or are they all added on to like each other?
They're all together. Like, so this one applies constant properties, and then this no generation is constant properties and no generation. So then this one is constant properties, no generation in one dimension. And then down here it's constant properties, no generation, one dimension, and steady state when we get down to here.
Okay.
Okay. So you could start at the top one and just do, let's say, up here on this, and if you just did steady state, all that would go away is this term, right? Okay. Generation, no generation is this term, right? 1D are these two terms, right? Constant property is the pulling of that K out. Okay, so that's where you start with this equation, and then you can simplify it from there, right, for your problem. All right, so we did this, right? We took our conservation energy, applied it to this differential control volume, and applied the Fourier's law to it in Cartesian coordinates and got this equation, right? We were able to get this, right? And what we should talk about too is these terms right here in the heat equation. Let me actually, so it makes it a little more obvious. Right here is our net energy, thermal energy into the control volume, right? So that's the net is from those terms. And then we have our generation and from our thermal energy storage, okay? And this all just deals with, temperature distribution in a stationary medium. Okay, so it's for conduction, right? So what is this useful for? If you want to know temperature in this block of metal or whatever it is, you need to know the temperature throughout something to know whether it's the right material to choose, right? So you want the right temperature and properties inside this material, making sure maybe it doesn't melt, you want the right heat transfer, something like that, then you might want to know the temperature distribution through something. So that's the heat equation. The other is, if you know the temperature distribution, let's say we took this heat equation and integrated it like I showed you in the last step where we integrated twice to just get a line. Now you know the heat flux through the equation, through this cube, because heat flux in the x direction is just the slope, right? The first derivative of temperature. So if you know temperature, then you can just take the derivative to get dt dx, right? And utilize the Fourier's law to get the heat flux at any point if you know what the temperature distribution looks like. All right. So here's versions, so you can do those same steps in cylindrical and spherical coordinates. So Taylor expansion, starting with the conservation energy, you have your cube. Taylor expansion, put in the Fourier's law for those, and simplify to this. It comes a little tricky. It's more on the geometry and not on those parts that I showed you. It's just being careful of kind of looking at like arc length and things like that on the geometry of what you're seeing for your cube. But it's really still COE and just applying the same things, okay? And you can do the same kind of simplifications to see what it is, right? Steady state simplifies this term out. No generation gets rid of that term. Right, and then if we were looking at one dimension, we'd get rid of those, right? If we were looking at two dimensions, we might include two of them, right? All right, so this now has constant properties. We can pull the K out, okay, but otherwise this is 1D right there. Steady state, no generation. All right, so here's, we kind of already did these. This is one dimension conduction, planar, so Cartesian coordinates, constant properties, no generation, and it becomes this because of the thermal diffusivity. Okay, we saw that in our derivation. The other thing you should look at is in this thermal diffusivity, you see thermal conductivity, which tells us about conduction, right? And then density times specific heat tells us about the properties of, the energy storage. So whenever you see these kind of ratios, just like Reynolds number and that you saw in fluids, you should always kind of think about what that means when the numerator is large or small, the denominator is large or small. So in this case, if conduction's large relative to the energy storage term, now we're going to have that heat being transferred through that medium very quickly, right? If we're starting with a block and we apply some heat to it, it's going to go through it very quickly, the conduction, okay? Or let's say the conduction is small relative to energy storage. So now when we apply that heat to that block, it's going to take a long time to go through that block, okay, to travel through it, because now that energy is stored, there's a lot of energy there for it to be put into it, for it to store it. Okay, so that's what kind of looking at this thermal diffusivity, what that means, right? And any kind of whenever you see a term that has ratios of things like that. All right, so now if we take this equation, let me rewrite it here. simplified heat equation we have. Okay. We take it, we look at it, we adore it, right? We shake our fist at it, and then we say, how can we solve this, right? To solve it, we need boundary conditions, right? We have an X direction, right? And it's second order, right? And you saw, and then we have time, it's in 1. So with it being transient, we still have time there, right? With X, we have 2, right? And you saw in my, let's go back to the notes that I did really quickly. You saw when it was steady state, right? We still had second order, but it was steady state, so we didn't have to worry about time in this case. And if we integrated it twice, we were going to get this equation, which has 2 constants, which means we need 2 boundary conditions to substitute back in for our constants, right? So we didn't know what's going on the boundaries of our block of metal, right? Okay, and this one we still have time, so we also need a boundary condition for time, but it's only the first order. So we just need the initial temperature distribution, okay? And most of the time, that's just saying, okay, the block is all at a uniform temperature, maybe room temperature of 20 degrees. The whole block of this steel or aluminum or whatever it is all 20 degrees Celsius at time of 0. And then we apply something to the boundaries, okay? The boundaries of X and on 0 and length of L, let's say. Okay, so we need 2 boundary conditions for the X as we saw, okay? And we have them here. We have 1, here's 4 choices we have for boundary conditions. 1, 2, 3, and 4, okay? All right, actually, I'll put this one over here. So let's go through. So the constant surface temperature one, okay? So this one is if we had a wall, let's say this is our wall here, okay, or our block of wood or block of metal or whatever it is, and time 0, it's all at the same temperature, then at any time after that, time 1, 10 seconds, 100 seconds, we apply constant boundary temperature here. So it has a surface temperature right there that stays the same no matter what time. And we have a different one on the other side, surface temperature 2. Make that a little easier to read. Okay, and we're holding those temperatures fixed. Okay, so no matter what time it is, we're holding that temperature the same. Okay, that usually can be done with, say, let's say you have steam on the surface or boiling, right? If you're boiling water and you just put that on the surface of something, it's going to stay 100, like boiling water at ambient, it's always 100 degrees Celsius, right? So that would be a constant boundary temperature on your pot that you're boiling that water, that surface there, okay? All right, so that's the first type of boundary condition we have, constant surface temperature. We have a different one, constant, number 2, constant heat flux. So that is, if we look at Fourier's law on this left boundary, so at X equals 0, if it's constant heat flux, this term is constant. It's not changing, no matter it's time, 1 second, 100 seconds, whatever it is, that is staying fixed. Well, that means for that to stay fixed on the right, the left has to be constant also on Fourier's law at that boundary. So K, the property, stays the same. That means this dt dx at X equals 0 has to be a constant. So, and that is the slope of temperature, and you see it here, right? This slope right there, at that point, is always the same slope. So it's always the same angle no matter what time you're at, whether it's time of 1 second, 10 seconds, 100 seconds, you always have that same slope there. Not the same temperature, but the same slope, right? Okay. All right, let's do 4 first. 4-3. If we have an insulated surface, okay, so that if we look at the heat flux equation, at x equals 0. If it's insulated surface, then that means we can't have any heat flux through it. So this is 0 on that surface. And for that to be 0, you know, this is just a property, so it's constant value. That means this has to be 0. Which means your slope of your temperature curve has to be 0 at that point, at x equals 0. So that's what you're seeing here. This is the slope right here. This point, x equals 0. It is 0 because there's no heat transfer going through that insulated surface. Okay. The other one that gets tricky is symmetry with it. So insulated surface or symmetry. Symmetry is the same as an insulated surface, and that one will require like us when we do a problem to it. But it just means if you had the same thing happening, let's say we had a block like this, but I'm going to call the middle section x equals 0, okay? And I'm going to have let's just put the heat flux, because I haven't done the convection one yet. So I have a heat flux here and here, and they're the same on both sides, right? First off, this block was at a uniform temperature, an initial temperature distribution through that block, right? And then we put this heat flux on it, okay? And it's the same on the left and the right. Well, you're going to have symmetry on your temperature distribution from the left of that dashed line to the right. It's going to be the same on the right as the left because it has the same thing happening on the left and the right. So you say the temperature distribution could look like this. Okay, so we have this constant heat flux on this side and this side, so the slope is the same. But then the slope in the middle is 0, right? We're heating it up. We're heating this piece of aluminum or whatever up with a constant heat flux on each side, so that heat has to penetrate to the middle, right? So it's lower in temperature here and higher here, okay? But it creates this slope right in the center. That's 0, and that's symmetry, okay? All right, and then we end up stopping again 5 minutes early just to get to the same place the earlier section did. So in this case, we have to finish our boundary conditions, and then there's just a couple more slides, and then the quick examples, and then we'll do examples on examples for the rest of the class, next class, and the following class. There's actually 2 classes of examples. Okay. All right. Any questions?
I had a question on the homework, but we can talk.
Yeah, we can meet in my office hours room. Okay. Any questions on the notes or anything from anybody? Well, then I'll stop there, and I'll see you in the next class. Okay, so we don't have class on Monday. Okay, so next class is Wednesday. Okay, no class. We have Martin Luther King Jr. Day on Monday. All right, so see you on Wednesday then. All right.
Thanks, Professor.
You have a, you have a
If